We've seen how to filter data frames and how to reshape them using Pivot. Let's now learn about Group By. We'll consider a data frame of sales of bread and butter. The rows correspond to sales made in certain locations on certain days. We could use Boolean filtering to find all sales made on Sunday and to count them. This requires knowing that Sunday is one of the values in the weekday column. Alternatively, we can group by the weekday column and count entries for each distinct value found. This is more convenient. In many cases, we would not know the distinct entries of the column. Let's look at that last command more closely. We're instructing Pandas to split the data frame into groups of rows using distinct values from the weekday column. For each value, apply the count method to that group of rows, and to combine the results in a new data frame with the distinct values of weekday in the index. The count method is an aggregation or reduction because it reduces many values to a single value. Pandas Group By works with many statistical reductions we've seen so far: the mean, standard deviation, sum, the first or last row of the group, and the maximum or the minimum of the group. Let's use split, apply, combine again. What was the total amount of bread sold on each day? Again, we group by the weekday column. This time, we're only interested in summing on the bread column. We can use brackets to select one or more columns over which to perform the aggregation. To see the sums of both bread sold and butter sold on all days, we use a list of columns in the brackets after the group by call. Pandas allows for multi-level group by passing in multiple column names in a list. Here, the result is the average amount of bread and butter bought at each of the two locations on Sunday and Monday. Passing multiple columns creates a sorted multi-level index. Thus far, we've used column names only within the group by. In fact, we can use any Pandas series with the same index values. For instance, let's create a series customers that tells us who made the purchases in our sales data frame. Customers has an identical index to sales, namely a range starting from 0. Then we can group by customers to split the sales data frame, select the bread column, and apply sum to determine how much bread each customer bought. The result is a new series with the customer name on the index. We'll close with a note about categorical values. Applying the unique method to a series returns an array of the distinct entries. To find out how many times each individual value occurs in that series, use the method valueCounts. Each of these distinct values is a category. Here, we transform the weekday column into a categorical type. In this case, the rows of that column have only two unique categories, and the series is of type category. Using categoricals has two advantages over a column of strings. It uses less memory, and it speeds up operations like group bys. For instance, in a large data frame, a weekday column could have, say, 10,000 entries with only, say, 7 distinct weekday values storable in less than a byte each, rather than a string. Behind the scenes, the series entries are stored using small integers and a separate lookup table. Now it's your turn to apply the principle of split, apply, combine in the exercises. Let's explore more about aggregation methods. We'll continue with the bread and butter sales data. We saw how to group by a column in a data frame and subsequently select one or more columns on which to perform an aggregation. For instance, here we compute the maximum amount of bread and butter from a single purchase in either Dallas or Austin. Dallas had the highest sale in both categories. That was a single aggregation. Using the AGG method, we can do several. We pass the list max, sum to AGG, and 2 aggregations are computed for each column in each group. The result is displayed using a multi-level index for the columns. Dallas also sold more in total in both categories. The AGG method can be used in several different ways. First, we can pass a list of strings representing common aggregation methods, for instance, sum, mean, and count. Alternatively, the AG method also accepts user-defined functions or library functions. Here, we define a function dataRange that accepts a series as input and returns the range in values from the minimum to the maximum. This is an aggregation because it receives a series and it returns a single number. The function dataRange can be used with AG chained to a group by and a selection. Here, we're seeing the range in the amount of bread and butter sold on each day. There was a large range in bread sales on Monday. Finally, the AG method also accepts a dictionary as input. The dictionary keys are column names. The values are aggregation functions to apply to each column. In this example, we group by customer. Remember, this is a series with a common index. We then select the bread and butter columns. We then aggregate with sum on the bread column and dataRange on the butter column. Only Alice made 2 separate purchases on Sunday, so her range in butter purchased is non-zero. It's your turn now to do some exercises with aggregations. We often want to group data and apply distinct transformations to distinct groups. Instead of aggregating after grouping, we can apply a transform method instead. This changes data frame entries according to a specified function in place without changing the index. As an example, let's compute a z-score. The z-score of a value is its distance from the mean of its population measured in units of standard deviation. This function is a transformation in that it accepts a series as an input and returns a conforming series. We'll use the automobile data from 390 automobiles manufactured from 1970 to 1982. We can apply the z-score function to the columns of the auto data frame, for instance, the MPG column, and look at the first few rows. Looking at the second row, this means the MPG rating of 18.0 for the 1970 Buick Skylark 320 is more than 1 standard deviation below the mean computed over all automobiles listed from 1970 to 1982. As an alternative, we might want to normalize the MPG data independently by year instead of over the whole population. We use group by year, we transform the values in each year using the z-score function, and then we recombine them back into the original shape. Again, we chain the head method to see the top rows only. In this case, normalized by year, the MPG rating for the Buick Skylark 320 is now only 1/2 standard deviation below average amongst cars manufactured in 1970. We know the AG method applies reduction and the transform method applies a function element-wise to groups. In some cases, split or by combine operations do not neatly fall into aggregation or transformation. For those cases, we use apply. As an example, we define a function z-score with year and name that receives a group of rows and returns a similar data frame with the z-score, the year, and the automobile name as columns. This new transformation is too complicated for transform, so we use apply instead. The output is the same z-score normalized MPG rating along with the name and year of manufacture for each automobile. Let's take a look at the function z-score with year and name again. This function is called 13 times, once for each year between 1970 and 1982, that is once for each group. We didn't select any particular columns after grouping, so all of the columns are retained in the subgroups used by the method apply. Within the function, the output data frame has 3 columns specified as dictionary keys. The dictionary values are selections from the input group. We transform the MPG column and take the original values from the year and name columns. After z-score with year and name has been called 13 times, the apply function recombines the outputs in a data frame with 390 rows. Now it's your turn to practice using transform and apply in the exercises.